Hi, everybody. Thank you for joining us today for the webinar on best practices in drone surveying presented by Daniel Katz. Please enter any questions or comments into the question box or the chat box, and we will address those at the end. Also, please save the date for our next webinar. It will be held on July 11th, 2018. The topic will be hybrid networks. And with that, I will hand it over to Daniel. Thank you.
Thank you so much, Kim. So as Kim mentioned, I'm Daniel Katz. I'm a co-founder of Aerotas. I'm going to be covering some details on best practices in drone surveying. A couple quick notes on housekeeping. I'm going to be covering a fair bit of information in a good amount of depth. If anybody wants it, so there'll be a lot of information on slides and what have you. Kim has said she'll send me the list of attendees after the fact, so I'll just go ahead and plan to send this actual slideshow presentation out to that list. So don't worry about furiously scribbling down notes or taking screenshots. I'll just plan to send this out after the fact. And as Kim said, go ahead. If you have questions throughout, feel free to put those in the chat box. Kim will collect those, and I'll do my best to leave about 10 or 15 minutes at the end to address those questions. If you do have questions that are more individual or specific to your operation or what you're looking to do, you can just go to that URL on the bottom there, go-aerotas.com, and submit your information, and my team will follow up, and we'd be happy to answer any other specific questions you have. So on that note, a word of background about Aerotas. Short version of what we do as a company is we work with surveyors to get the maximum benefit out of drone technology. Obviously, this technology has a ton of potential, but as I'm sure a lot of you who are here are experiencing, it takes a lot of know-how and a lot of nuance to get it right and to really maximize that benefit. Generally speaking, we do two things. We help teams start up and running with drone programs, provide training, provide the equipment, everything else they're going to need, and then we help them get to line work on every project by providing data processing and CAD drafting as a service. So that's a little bit of background about us and kind of the what has led us into learning a lot of what I'm going to be walking through here today. So basically, I want to share with you some of the hard-learned lessons that we have learned about how to build and operate a drone program for survey applications. So big picture, first thing to understand is when thinking about using a drone, you actually need to think about it as being part of a complete drone program. And a drone program consists of 5 key components, and I'm going to walk through each one of these through the course of this webinar. First up, anybody who's going to be flying the drone needs to have a license, needs to know what the regulations are that you're interacting with and how to comply with those. You need to get insured specific to your drone operation. You need to have clear standard operating procedures that are guiding how that data collection is being done using the drone in the field. Then obviously you need to have the drone itself and all the other kind of supplemental gear you need to operate that drone. And then last and probably most critically is you need to have a good, efficient way of actually getting to final line work. And this is an important kind of level set. A drone should not be just a marketing tool or something that's getting you pretty pictures. Used right, a drone absolutely can be and should be a survey tool. It should be enabling you to get to final topographic or planimetric survey deliverables. So go ahead and walk through each one of these in turn. That last one, the actual line workflow, I'll even show a quick example of what we have found is the most efficient way to get to that line work. Starting at the top with the license, anybody who is going to be actually flying the drone, the quote-unquote pilot in command, must have a special drone pilot license. Most commonly, this is referred to as the Part 107 license. It's the body of FAA regulation that governs this. I also see it referred to as the RPIC, Remote Piloting Command certification or license. What it takes to get this, it actually just takes passing a knowledge-based test that is administered by the Federal Aviation Administration out of any one of about, I think they have 500 testing centers in the country. So it's just a knowledge-based test. Doesn't actually require going out and doing any practical tests. It's not like your driver's license where you have to go and show that you know how to drive the car. Having said that, it is pretty technical. So good rule of thumb for this, anybody can pass this test, but you do have to expect that you're going to need to do some preparation and some studying before going in. Think of it like your driver's license test the first time you had to take that test. Totally possible, anybody can do it, but it does definitely require, for most people, a fair bit of studying and preparation. There are a lot of resources out there that can help get you through this process. The FAA actually put out a handy study guide, which is 600 pages long. So I definitely recommend looking for some more efficient resources. I know a lot of local community colleges have started offering courses specific for prepping for the drone pilot license exam. There are also a handful of providers who offer online courses. You should expect to spend on the order of 4 to 8 hours worth of studying in order to be able to go in and pass the exam. What's nice is the exam, you'll actually need to get a 70% on the exam in order to that's considered a pass. So it can be helpful to, there's some areas of information that are completely irrelevant for actually flying a drone that really get into the nuts and bolts of how aviation works. And it can be okay to say, you know what, this stuff's really complicated, this specific topic, I'm going to go ahead and just plan to get that question wrong. I'm going to focus my energy over here where I know I can study up on these topics and get those questions right. Ultimately, what matters here is that the person who is out flying the drone has that license. It's their ultimate responsibility to make sure the operation is safe and legal. And so that means they also have to have good understanding of how the regulations work in terms of the projects that they are doing. Next up is insurance. Now, the reason that drone-specific insurance is important for most survey operations is because pretty much every standard commercial liability policy has an aviation exclusion. And this is a clause in that liability policy that says pretty much if it flies, it's not covered by this policy. This obviously comes from the legacy of manned aviation, which is fairly higher risk profile, but it does apply to drone operations as well. So you basically need to get a policy that will plug that aviation exclusion gap in your current coverage. This is becoming fairly easy to get. Most commercial brokers will have a way of going out to the market and securing a policy. We really like working with a company called Transport Risk Management, who manages the large majority of drone policies in the world. We find, in our experience, it winds up being a bit more cost effective and get better service if you go with a kind of purpose drone specific provider. Ultimately, there are two types of coverage that you want to put in place: liability and what's called hull. Think of this like car insurance, where you've got your liability coverage and your collision insurance. So liability obviously covers if the drone does damage to something else, if it runs into a light post and the light post needs to be repaired, or if somebody trips over it in the office and hurts themselves. Hull coverage is like your collision insurance in your car, where that is going to be the coverage that kicks in to cover the cost of repairing or replacing the drone itself. So if, again, you run into that light post, this will kick in to cover repairing or replacing the drone. Or even if the water main down the road breaks and your office floods and the drone's destroyed. So this is generally what we recommend putting in place. Pretty good benchmark for liability. Most companies are good with about $1 million policy. That's kind of proving to be pretty standard. Next up after insurance is what is often one of the more important components to a drone program actually being successful, but that is most often overlooked in our experience. When we work with surveyors who have some degree of a drone program in place, maybe they've gone out and they've bought the drone and they've tried using it on a couple projects, usually this is the component where they are struggling the most, and that is holding them back the most from being able to actually use this as a survey tool and rely on the data they're getting out of it. So standard operating procedures, they're not sexy, but they're often the most important thing for driving viability and profitability of this tool. Ultimately, the importance of standard operating procedures is that they allow your operator to sidestep stumbling blocks that are likely to come up, the ones that are predictable and the ones that are less predictable. Ultimately, these SOPs should make sure that every operation is legal, that it's safe, it's efficient, and therefore profitable, and that, most importantly for surveyors, it is accurate and gets you repeatable results. Now, what standard operating procedures actually cover is frankly a lot. All of this ultimately, the ultimate goal, like I said, is getting to good, repeatable results. You want to have your field operations standardized so that regardless of which surveyor goes out, regardless of whether it's Tom, Sally, or Harry who's taking the drone out today to do the data collection, you're getting equivalent, comparable results back. The data that is going to be collected is going to be collected in the same way, so you can get expectable, consistent results. So the challenge with standard operating procedures, and say this from the experience of us having developed these, is that they need to be both comprehensive and simple. So I kind of threw a laundry list on here of the kind of things that should be covered in standard operating procedures for drone surveying, everything from ground control planning in terms of layout marking to how you set up the flight plan, set up the autopilot and the mission, all the pre-flight preparation that needs to happen from the legal side, from the equipment side, basic kind of guidelines and walkthrough of executing your standard survey mission, and then also how to deal with things going wrong, unexpected emergencies happening, a low-flying emergency helicopter coming into your project area, and then after the project, walking you through all the post-flight things that need to happen, making sure you're logging everything you're doing, record keeping, and doing the basic maintenance and good storage practices. So this is something that I often encourage folks, but before you even go out and start shopping for a drone, this is a good place to put your energy first, because your standard operating procedure is going to guide you towards understanding what is the actual drone that you need in order to execute on the projects that you're trying to do. Now, on that note, it's like I said, the drone often is less important than those standard operating procedures, but obviously picking the right drone is important. We have the benefit as a company of we're not formally affiliated with any specific drone manufacturer or any provider of anything. And so that allows us to do that intentionally to kind of maintain flexibility, maintain independence, and the ability to go out and audit and analyze everything that's on the market to make sure that we're choosing the best tool to provide to our customers. So I want to walk you all through is basically what our kind of analytical processes, our decision-making criteria for assessing the equipment on the market to decide what is the best drone tool for most surveyors to use. An important level set here is when you start out looking at technology, the most tempting thing to do, the most intuitive thing to do is start looking for tech specs. To look for every drone you can come across and try to get all of the technical specifications on that drone about everything you can figure out. The wingspan, the flight time, the voltage of the batteries, what have you. But ultimately, what matters is not necessarily those individual tech specs, not even the ones that seem completely critical, like camera resolution. What matters is what is going to get you the results that you need. So for surveyors, the foundation of that, the thing that matters more than anything else is going to be accuracy. So what we always encourage is start this process, and this is what we do when we're evaluating tools. We need to start with, what is the actual field tested accuracy of this drone? Regardless of what the laundry list of tech specs says, what kind of accuracy can we expect out of this drone based on ground truthing and field testing over what amount of acreage per hour? Obviously, if I can get down to 300ths, but I can only cover 100 square feet per day, it's not going to be an efficient tool. It's not worth the investment. So it's actually that kind of accuracy by acreage by hour. How much ground can you cover per hour at what level of accuracy? Ultimately, the only way to do this is with field testing. Strongly encourage folks to always go out and ground truth and field test the tools that they're considering using for survey work. once you've kind of assessed and found, maybe there's a handful of drones that can get you that accuracy by acreage you need, next thing to think about is reliability. And obviously reliability matters because you need to know that every time you take this tool out, you're going to be able to use it. You're going to be able to get the results that you need. And you're not going to have to be replacing it before you can make your money back on it. Now, often the way we approach reliability is actually to think first about simplicity. Now, simplicity matters not because people are dumb and they need a tool that's super easy to use. Simplicity matters because a simple tool is less likely to break. Fewer moving parts, fewer complications to it mean that there are fewer ways for things to go wrong. So you want something that's going to be easy to set up for the first time, easy to go through those field projects, setup processes, require minimal maintenance. In part because that's going to mean that you're getting the efficiency that you need. It's getting you to that. It's providing that time savings in the field, but also because it's going to mean you have the least chance of things going wrong, and the least likelihood that you get out onto a project site after driving for 2 hours, pull the drone out of the case, and something goes wrong, so you can't use it, and you have to come back another day. You've now lost a lot of that ROI time savings benefit of this tool. Then obviously the last criteria to consider, the last factor, is price. Obviously, it's buying an incredibly expensive tool is less helpful for a business because it puts you in a deeper hole for getting to positive ROIs. It's harder to get that return on investment. It's not that expensive tools are bad. It's that it puts you in a high pressure situation in the business. You have to figure out how to absolutely maximize your utilization of this tool, how to charge extra for it so that you can earn back that investment. If instead you can find a drone that is going to get you that accuracy and that reliability at a lower dollar point, that's relieving a lot of that pressure and making it easy for this to become a profitable tool and something you can use automatically without having to have that business pressure. And when thinking about price, it's not just the price of the airframe itself, but it's the all-in cost, including, of course, the sensor, but also all the support equipment you're going to need, spare batteries, replacement propellers, the rugged carrying case that you want to be able to put this in so you can throw it in the truck, and then also insurance. Similarly, again, the car insurance, the main driver of cost in drone insurance is going to be the cost of the actual airframe. So cheaper drone means cheaper insurance. So this is kind of how we approach analyzing all of the components that go into the physical kit of using a drone program. So with that, I'm going to walk you all through a few of the key components that we get the most questions about, which are options in terms of drone airframes, in terms of the actual sensors that those airframes can carry, and then options for georeferencing, how you actually get to that corrected anchored model. And again, this comes from we don't have a dog in this fight. I'm not I don't have somebody sitting behind me saying make sure you kind of endorse this type of tool. This is based on us going out and doing our independent evaluation of the market, which has resulted in us choosing or providing the technologies to our clients that we do. So in terms of airframes, broadly speaking, you can consider 3 different categories of airframes. You've got small multi-rotors, large multi-rotors, and fixed wings. Multi-rotors are going to be basically fly like helicopters. They take off and land vertically. They can hover in place like a helicopter. They can make tight right angle turns. They can fly really slowly. Whereas fixed wing is going to fly more like an airplane. Takes off at a slope, flies in kind of makes longer swooping turns, comes in and lands at a slope. Small multi-rotor, kind of best in breed, is the DJI Phantom 4 Professional. This is, kind of spoiler alert, this is the drone that we have found provides the best results. This is the one that we provide to our clients and recommend. There are other small multi-rotors out there, of course. Generally speaking, they're going to be around 1.5 feet in diameter, so fairly small, really usually only a couple pounds. All in, so think about that all-in cost, including the sensor, including the supplemental equipment you need, including insurance. It's going to be on the order of about $4,000 at the end of the day. And the accuracy you can expect with, again, the right standard operating procedures in the field, the right data workflow would be a tenth, or sometimes even a bit better than a tenth vertical. Large multi-rotors, kind of the industry leaders here, again, DJI with its M200 series, Matrice 200 series, or the 600 series. Micro drones also is another kind of leading provider of these larger multi-rotors. These are going to be more like closer to 3 feet in diameter, so substantially larger. On the range of, depending on what they're carrying, anywhere from 10 to 30 pounds. All in, it's pretty wide range, but can easily be well above $20,000, even up to upwards of $70,000-$80,000. Accuracy is also going to be kind of field truth accuracy. Expectable accuracy is going to be similar to the small multi-rotor at about a tenth. Fixed wings, kind of more common ones here. Trimble has their UX5, or SenseFly has their EB. Going to be about 3 feet in wingspan. Usually they're made out of this pretty dense foam, so they're fairly light. Similar weight actually to a small multi-rotor. Considerably more expensive. I think there are some models that are as inexpensive, about $25,000. They can easily get upwards of $60,000 to $70,000. And these are going to be sufficient for getting the accuracy you need for contouring in general. So let me walk through kind of the trade-offs with each of these airframes. So the main benefit of a small multi-rotor, this shouldn't be surprising to hear based on what I walked through in terms of our kind of analytical framework. Super easy to use, super reliable, really inexpensive. Particularly that Phantom 4 Pro, it just works. It's the most produced aircraft in history, so it's they're able to make it for really cheap. They've worked out all the little kinks, so it's the most reliable airframe on the market. Your main drawback is going to be that it's less flexible. It actually has a built-in camera, which is pretty common on these smaller multi-rotors. So you can't swap that camera out if you decide that you want to use a different type of sensor down the road. Really, this is one tool for one type of job. That's kind of the trade-off with it being, because it's this closed system. That's a big part of what makes it so reliable, so inexpensive, and so easy to use, but also means that it is less flexible. In our experience, for most surveyors, most survey work, most projects, this is going to be the right tool for the job. It's okay that it's not that flexible because it can get you the accuracy you need on most of the projects that you'd be looking to do. Large multi-rotors, main benefit of these over a small multi-rotor is going to be how customizable they are. Yeah, you can, these are more flying platforms that you can swap sensors onto. You can really modify them to whatever you need. That does come with the drawback of them being complex and expensive. They are much more involved to use, even to set up for the first time or to use in the field. Complexity means things aren't going to work sometimes, which means you're going to lose time. A quick anecdote on that front. We recently had a local engineering firm that had a DJI M600. They're one of the premier engineering firms in the country, or in the region. And they refused to believe us. They did not believe us that a Phantom 4 Pro could get as good accuracy as an M600. So we decided to go out and kind of do a side-by-side comparison. So we set out a test site, went out there on the same day. We went first with the Phantom 4 Pro. It took about 15 minutes to set it up, fly the site, pack it in. Everything was pretty simple. They wound up having to come back 4 times with their M600 before they could actually get the data collected. Because each time they go out, something wouldn't work right. Whether it was the interface between the drone and the big camera they had mounted onto it, some issues with software. There's so many moving parts in the drone that I wound up taking them 4 field trips to actually get the drone up into the air and collect data. And again, these are very, very sharp folks. They have a lot of experience with drones. These are just really complex tools. And then ultimately, when we did get the data, half the photos were blurred and nobody could figure out why. So ultimately, for the best case, the right time for using these types of larger multi-rotors are going to be if you have the need to do something really specialized. Your business involves doing roof inspection as well, where you need to be able to mount a thermal camera sometimes so you can see what heat's leaking out, or bridge inspections, so you need to be able to put a top-mounted camera on to look on the other side of the bridge. But I would even consider these as even if that's part of your work, I would still use a small multi-rotor for your bread and butter survey work, and then this large multi-rotor is your tool for those specific projects. With a fixed wing, your main benefit is going to be flight time. An airplane-style airframe is just a fundamentally more efficient way of flying than a multi-rotor, so they can stay aloft for a lot longer while using less energy. It means you can cover more ground. Unfortunately, that benefit of range is negated by the state of regulation right now. So one of the main kind of laws governing commercial drone use is that you have to keep the drone within line of sight the entire time it's flying. And frankly, a small multi-rotor can already fly further than you can see it. So in most cases, having that ability to cover a ton more ground, you can't actually take advantage of it. In addition to that, there are a couple other drawbacks to be aware of. Fixed wings, by and large, when they fly, when they land, they belly land. They come in and they basically just kind of land on their, come in and land at a slope on their belly, which is great as long as you only ever do projects on nice manicured golf courses. Obviously, if you're landing in dirt or on asphalt or things like that, the airframes get chewed up pretty quickly, and because the camera is mounted into the airframe, it doesn't take more than a poorly placed small rock in order to do some serious damage to a sensor. They also are capable of substantially lower accuracy than multi-rotors are. The reason for that is some of the kind of physical dynamics of how fixed wings have to fly. Fixed wings have to maintain a minimum flight speed in order to stay aloft. They have to fly fairly fast in order to keep flying, and that means that they have to fly pretty high so that you don't get bad motion blur on the ground. And they can't carry a terribly large sensor because because weight is so critical on a fixed wing. So you wind up having to fly high with a fairly small sensor, so your ground resolution is pretty low, meaning your accuracy is also fairly low. Also, whereas a multi-rotor can carry a gimbal that allows, basically the camera is mounted via gimbal to the airframe that allows the camera to move independently of the airframe. So when the drone is turning, when it's fighting wind, that gimbal keeps the camera pointed straight down even while the airframe is moving around it. Fixed wings generally don't carry gimbals, and so you have the sensor, the camera, basically just built into the airframe. So any little kind of shudder you get from the wind or when it's turning or anything like that winds up causing blurring or distorted data. So ultimately, though, there certainly is a place for fixed wings if you're regularly doing really large projects in areas where you can maintain line of sight for as far as possible. It can be the right tool for the job. Again, most surveyors figure most projects under on the order of 250, 200 acres. Small multi-rotor can get it done pretty well. Next up is sensors. Broadly speaking, got three kind of sensors. Cameras that are built specifically for drones or for the drone. These are going to be certainly those that are built into your small multi-rotors, as well as, for example, DJI again has a couple different cameras that can be swapped onto a couple of different airframes. Usually with your airframe, including the airframe, these can be as inexpensive as $1,500 on that Phantom 4. Again, accuracy of about a tenth. Another option are these larger kind of third-party cameras that are mounted generally on the larger multi-rotor airframes. These are going to easily, including that airframe, run on the order of about $20,000 and get you equivalent accuracy. And then, of course, everybody always wants to know about LiDAR or kind of aerial laser scanners. These are going to run you on the order of about $170,000 plus, and are capable of about 2 to 3/10 accuracy. So again, quick walk through the trade-offs here. Shouldn't sound surprising. Benefits of those drone-specific cameras or built-in cameras on the small multi-rotors. They're easy, they're accurate, they're inexpensive. They get you good results without too many headaches. And again, your drawback is going to be less flexibility. You can't put, certainly on a small multi-rotor, you can't put any sensor under the sun on it. You really just are limited to the sensors that the drone manufacturers produce. Similarly to what I said, our analysis of the small multi-rotors, Right now, this is going to be the right tool for most surveyors and most survey projects. Getting one of these cameras that is designed to work with the drone so that you have the least amount of chances of things going wrong. Those larger third-party cameras, benefits are going to get you also that equivalent accuracy of about a tenth, or capable of a tenth, but they are also going to get you higher resolution imagery. Basically, you can fly higher in order to get that accuracy. And they also have the benefit of flexibility. These are going to be sensors that you can swap out with something else because you're generally carrying them on one of those larger multi-rotors. The drawbacks, though, are going to be, again, your reliability. Because you are mounting a third party, you're trying to get two independent technologies to talk to each other, there's going to be substantially higher likelihood of things going wrong. A lot of times, for example, the way that on a large multi-rotor airframe that one of these large cameras is triggered is by a physical servo, physical little switch that actually pushes the shutter button. So it doesn't take much for that to get slightly off kilter, and then the drone isn't taking pictures. Ultimately, this is good for, if for your business there is a particularly compelling reason that you need really high resolution ortho photos. That's the main benefit you get of using a large camera over one of these smaller drone specific cameras. Your accuracy is going to be the same. The reason being, with a large camera, you have to fly higher than with one of these small built-in cameras, because with that larger camera, you get a lot. If you fly it low, you get a lot more artifacting and warping of the image. So you have to actually fly higher in order to get that equivalent accuracy. But you get high resolution imagery at that higher altitude. LiDAR, main benefit is you can shoot through some ground cover, some limited ground cover. Which obviously is nice for, if you're doing projects that do have some sparse ground cover. But right now, there are a ton of drawbacks to this technology. It is still pretty new, so there are a lot of reliability issues that we've seen in the field. They require a ton of maintenance. Managing this data is really cumbersome. You've got massive point clouds that you're now having to work through. And the accuracy is not great. In order to get even to close to a tenth accuracy, you'd be looking at about a $500,000 system. In field testing, the less expensive $170,000-ish dollar ones accuracy comes in at about closer to 3/10. So it's right now this is very much one that we're excited about, but our recommendation is to wait and let the technology mature. But for teams who are extremely experienced with both laser scanners and with drone technology and regularly do work in some sparse vegetation, it could be a good investment today. All right, last up on this kind of technology overview is georeferencing. Basically, in order to anchor the model down to correct it, there are two ways to go about this. One is to use basically a drone with standard onboard GPS, consumer grade GPS, but to rely on ground control or aerial targets to actually anchor it down. The other alternative is to use a basically survey grade high accuracy GPS on board that drone. Using ground control, generally similar to how you'd work with a conventional aerial surveyor, setting targets out on a project, surveying those into high accuracy, and then anchoring the model down to it. The benefit of it is it's something every surveyor knows, pretty much knows how to do this. And it just involves setting a mark on the ground or using a photo ID point and surveying it using your conventional equipment. So it's, doesn't add that much cost to a project. It's pretty straightforward to do. The drawback is you are having to collect more field shots. Given that the main benefit of a drone is that it reduces the amount of field work you have to do, that is something to keep in mind, that you're now adding some field shots you have to collect. In our experience, for most surveyors, most survey work, setting ground control isn't so cumbersome as to be negatively impactful, so it's generally our recommendation. The other option is there are providers that make basically survey grade, dual band GPS, onboard GPS systems that allow the drone to know its location to extremely high accuracy. These are basically onboard RTK or PPK or direct georeferencing. What that means is the location of the drone when a photo is taken is known to extremely high accuracy. And the implication of that is you can set less ground control. You do absolutely still need to set some ground control, in order to make sure that you're on your right coordinate system, that you aren't having any faults, that in order to actually anchor the model down, you do still need some ground control, but you need a lot less, on the order of, particularly larger projects, could be a 60 to 75% reduction in field shots. But there is still kind of a minimum number of ground shots or ground control shots you need in order to be able to be confident in the model. Downside is, again, complexity, both on the equipment side and on the data side. Getting from location of drone to the location of the center point of the photo is very complex. I know, talking to our data processing team, we've only seen one, who worked with one surveyor who had good data collection practices on this. It's just very complex to marry together all these different data streams you have to in order to get to the accuracy and consistency that you need. So again, for most surveyors, most survey work, relying on ground control is going to be the best way to go. But if you are regularly doing very large projects, figure, again, 100, 200 acre type projects, and have a lot of experience with custom drone hardware, this definitely can be a time saver and a money saver. So summarizing all this, taking a step back and thinking about the so what, basically our recommendation right now is to start with what's known, start with what works, is an inexpensive investment, gets good results today. Use that to build proficiency and let these other technologiis mature for a little bit. It doesn't make sense to just sit on your hands and wait until the day when LiDAR is perfect and direct georeferencing is the data workflow is optimized, because you're losing time to, first of all, be profiting from the time savings of using kind of an inexpensive drone today, and you're also not building that in-house proficiency and that learning about integrating a drone into your workflow. So again, our recommendation: small multi-rotor with a built-in camera. 20 megapixel camera is kind of the minimum technical standard on a gimbal, and plan to georeference that via ground control. So with that, I have to move pretty quickly here, but I do want to walk through what it actually takes to then use a drone. The workflow we found is best for using a drone on projects and actually getting to that final line work. Broadly speaking, you got 5 steps that you need to go through: setting those ground control targets, then actually flying the drone and doing the data collection, taking those raw photos that come out of the drone, going through the photogrammetry process and that photo stitching, extracting line work, effectively reducing that photogrammetric model down, and then bringing that over into CAD and finishing the survey. Ground control, like we talked about, the reason this is important is because you need it to anchor the model down. When you stitch those photos together, that's kind of floating out in space. The drone does have, even these inexpensive small multi-rotors have onboard GPS, but they're consumer grade GPS. It's mostly for the purpose of navigation. And so it does its best to use that to geolocate the project, but you're going to be off by GPS error. And a lot of times can have some warping in the model. So basically, ground control points, or these targets, are like nails that you drive through the model to anchor it down to your coordinate system. Because ground control is kind of your critical first step in ensuring that you get to the accuracy you need. There's a lot of nuance that goes into getting ground control layout correct to get to the accuracy you need. And it's essential because effectively the accuracy of your ultimate model is going to start with making sure you have the right density and layout of control. This is a big thing that is important to have codified in those standard operating procedures and have your people trained on, is knowing how to approach a project in terms of where my ground control needs to be. Ultimately, what actually takes to set that ground control once you've decided where they need to go, not that complex. Fairly similar to working with a conventional aerial surveyor. Basically, you just need to have targets on the ground and survey those into high accuracy. You can use photo ID points, but we actually love linoleum kitchen tiles. Black and white checkered linoleum kitchen tiles are 10 cents at Home Depot, and they're super easy to pick out of the photos. And most importantly, have a very, very, very clear center point. You want to make sure that the exact same spot that your field surveyor is locating that ground control target is the exact same spot that in the photogrammetry process you're going to click in order to plug in those coordinates. Rule of thumb, when using particularly those, the Phantom 4 Pro, is 5 targets per battery. Not necessarily, it doesn't make sense necessarily to think in a number of targets per acre because it depends on the height that you're flying. So if you operate on the assumption of 5 targets per battery, that's going to get you close to what you need. Realistically, when you're out in the field setting these targets, you've got your field survey equipment out there anyway. This is when it makes sense to also just go ahead and shoot any targets or any field shots that you're not going to rely on the drone for. So any shots you need higher accuracy, building corners, ADA ramps, as well as anything that's going to be obscured from the air. So utility under a tree cover or something like that. Once you've finished that, going out in the field, doing that setting control, you come back and you go through your actual drone setup. There's another place where those standard operating procedures are essential. And best practice here is to effectively have your standard operating procedures codified into a simple one-page checklist that your field surveyor can use to make sure that they're going through all those steps that they need to. It's going to take them through all that pre-mission setup, maintenance, calibrations, and the like, and make sure that, again, you're getting consistent data back. You're flying this mission the same way no matter who's going out there or what day it is. What it actually takes to do that setup in the field, if you have good SOPs and a good checklist, is pretty quick. You've got a couple minutes worth of calibrations on the drone and setup, and then you set up the autopilot. If I pop up this screenshot on the bottom right, it's a screenshot from the autopilot we recommend, or that we provide to our clients. It's basically a software that lives on an iPad that's attached to the controller. And you're basically looking at a Google Earth type interface. And effectively, all you need to do is trace the outline of the area that you need to fly and set your flight altitude. It creates its own flight path. And then surveyor hits go and keeps an eye on the drone while it's flying. The complete operation is autopilot controlled. Now, a critical part of the decision-making process in actually setting up that flight plan and doing the mission planning is determining what accuracy you need for that specific project. So I have up here a summary of a ton of field testing we have done with the Phantom 4 Pro to establish some benchmarks of accuracy expectations. And the first thing you'll see is that there's a trade-off between basically that second column and that third column. The amount of ground you can cover per hour, per unit of time, and the accuracy you can expect. Excuse me. The reason for that is if you need to cover more ground, you need to fly higher. Basically flying higher, then each photo is covering more acreage on the ground. But that also is going to mean that your effective ground resolution, your ground sampling distance is reduced, which is going to have substantial impact on your final ground truth accuracy. So if you've got a project that's on the smaller side, or you can afford to spend a lot of time on, and you need to get to that 10th level accuracy, you fly low, and you can cover about 25 acres per hour. But if you're doing a project where all you need is contours, you need 1 foot contours, so you need to have be accurate to within half a contour interval. It doesn't make sense to. There's no need to spend the extra time in order to get that higher accuracy. You can fly the drone up at your legal ceiling of 400 feet and cover about 10 times as much ground per hour, about 250 acres per hour, and you'll be at, based on our testing, 4/10 or better vertical. So certainly good enough for that half foot or for those 1 foot contours. So this is kind of a critical thing to build that institutional knowledge about and build into your SOPs is thinking about our project. What do I actually need? What is my final deliverable here? So what does my accuracy need to be? What can I afford to do in terms of field time? And then optimize that mission planning, that altitude planning based on what those ultimate accuracy needs are. Once the field operation is collected, you basically are completed. You have effectively collected a whole bunch of photos. You need to stitch those photos together into your 3D model. And there's no two ways around it. Frankly, that photogrammetry process it's hard. It's very technical. It's kind of the most technical part of this process. For just kind of frame of reference, the computers we have that we use to do this data processing, these are pretty much high-end gaming computers that have top-of-the-line CPUs and GPUs or graphics processors. About $4,500 computers, and when we're running these photogrammetry projects, running that photogrammetry software, it pretty much maxes out those computers. You can't really do anything else at the same time. And that actual software we use is Pix4D. It's one we found is kind of best in breed. The perpetual license for it is $9,000. But the most expensive part of this process is definitely the man hours. Even for we've got folks who live and breathe this stuff, and even on a 5-acre project, they're spending at least 45 minutes and entering in ground control, running QA/QC, and then these really high-powered computers are cranking away for a few hours just to do that photo stitching. So it's important to have that level set and know going into it this is really complex, but you do have options. What we always encourage our clients to do is have the ability to use all these options based on the specific project that you need. So build in that flexibility. Generally, you've got kind of 3 options about how to get this photogrammetry done. You can use kind of an automated outsourced service. You can do it in-house, have that software yourself and do it, have your people running it, or use kind of like a hybrid or specialized service like what we provide. Those automated services, these are ones where you're basically uploading photos to the cloud. They're going to a server. That server crunches, does all this automated processing and sends it back to you. These are going to be your drone deploy, your 3DR site scan. Your main benefit is they're going to be quick and easy. Usually can get you something back within a matter of a couple hours. But your main drawback is going to be accuracy. So these don't have a human in the loop. There's no QA/QC being run on them. Nobody can actually go and optimize the project settings based on that project need. So the accuracy is not going to be great. However, there absolutely are applications where these are a great resource. If you're doing a project where you just kind of need to be monitoring a construction site or something like that, or you just need a quick excuse me, low accuracy planning map or something to include in a bid or something like that, is a great way to just as easily as possible get yourself something. And when it doesn't need to be high accuracy, it's kind of the quickest and easiest way to do that. Kind of the other end of the spectrum is actually having the software in-house, having Pix4D or Datamate or Data Survey or Agisoft, actually buying that software, renting that software, and having your people in-house do that data processing. The main benefit that's going to give you is flexibility, particularly around timelines, since you can basically choose how much of your staff's time to commit to it. Main drawback is, like we just talked about, it's hard and it's expensive. The learning curve is pretty steep and pretty long, and your people's time is not cheap. But it's good to, over time, to try to build enough of the capability of running the software that you can do it when it makes sense on a project. We have clients who do work for the military, and so they have very, very strict data custody rules. So they need to be able to do those projects in-house. Then they'll shop out the kind of bread and butter ones to us or to somebody else. We're kind of a hybrid solution in that we are an outsourced provider of that data processing. There are other companies that do this as well. Difference between us and those automated services is going to be that we actually have a human in the loop, managing ground control, running QA/QC. We catch errors about 15 or 20% of projects, anything from a mismarked ground control target or a ground control point target that was kicked and moved, through to little bugs in the software that we catch and correct for. So main benefit of somebody like us is going to be accuracy, but that does come with a time cost. So whereas these automated services like drone deploy can turn something around in a couple hours, for us it's often a day, 24 to 48 hours to get that photogrammetry done. Now, regardless of how you do that photogrammetry, I have to cut some of this a bit quick. I realize we're coming up on time. I want to make sure I leave a few minutes for questions. So let me just speed through kind of the end of this workflow. Regardless of how you do that photogrammetry, you're going to get the same options of outputs. A point cloud, which is actually how the technology of the software uses to actually do that photo stitching. An orthophoto, and a digital surface model. Digital surface model is effectively, think of it as kind of a 3D mesh over the top of that point cloud. Now, the challenge, this kind of next step is one where we see a lot of people struggle. The problem with those outputs that come out of photogrammetry software are great, they're beautiful, but they're not a survey, and you need to have a way of actually getting from that to your actual CAD survey. Problem is, if you actually try to open that point cloud or that orthophoto or the digital surface model in CAD, it's going to break it. CAD is just not designed, it's not optimized to handle these super, super high resolution, dense 3D models. So you need to have a way of reducing down that model into a CAD-friendly surface. Now, our preference is we avoid point clouds whenever we can. Now, you can take a point cloud and basically put it through kind of a dumb decimation process, have it kind of like remove 1 out of every 1,000 points, have it do some automated automated software-based classification of those points. But going through that data reduction is really, really labor intensive, and those softwares are complex and expensive. The way we prefer to work is to use a software called Virtual Surveyor, where we take that digital surface model, which is a kind of a mesh over the top of the point cloud, open it into Virtual Surveyor, and then when our team does line work for clients, they're basically just drafting over the top of that 3D model, that digital surface model. So looking at the screenshot on the right here, you can see basically they click to add these spot elevations. You're basically just clicking on the model and effectively surveying on top of it. And you can just draw in your line work, draw in your curb line, draw in your paint striping. Again, very similar to as if you were out in the field actually surveying on the site. And then what you output from that is a CAD file, a DXF or an ASCII file. When you bring that into CAD, it comes out basically looking like standard native CAD data. And this is kind of an important benchmark to set, is that your ultimate output, the ultimate thing that comes out of this drone survey project, should look indistinguishable from if you had done that project conventionally via any other means. So by using that Virtual Surveyor software to effectively draft on top of digital surface model and export out a DXF, when you bring this over into CAD, you're basically just looking at CAD data. So I'll go ahead and wrap it up there. Kim, again, if you have any other questions, happy to address those. Kim, were there folks who had submitted questions that we want to take a couple of minutes to respond to?
Yeah, I have one question here, and in the meantime, if you guys have any questions, feel free to enter those into the chat or question box. The first question I have is, can you please define what you mean by accuracy? Are you meaning a surface accuracy of 0.1 or just horizontal?
Oh, that is a very, very good question. We could certainly talk for another hour on that topic. The standards of accuracy that we use are the ASPRS positional accuracy standards. This is how we approach evaluating accuracy of a drone. ASPRS is the American Society of Photogrammetry and Remote Sensing. Their positional accuracy standards are basically guidelines for setting a set of, I think it's a minimum of 25 field shots that you basically then just measure against the model. So on every one of those points, you say, okay, from the 3D model that came out of the drone, my XYZ is this. From when I survey that on the ground using my total station, my XYZ is that. Measure the delta between those measurements, and then do that across all that whole network or all of those different checkpoints on the project site, and calculate the root mean square error of those differences between your field check shots and the measurements that came off the 3D model. And that basically gets you that RMSE, or that RMS error is a tenth or better when we've done those evaluations. So hopefully that was enough of a question. If that person wants to talk afterwards in a bit more depth, I'd be more than happy to.
Okay, thank you. Next question, what software do you use for the line work and spot elevations?
Yeah, the software we use, I'll bring it up really quickly. It's called Virtual Surveyor. So this is what we use in-house to do that line work for clients, and what we recommend for clients who want to do it themselves. It's a very, very quick version. I brought it up on my screen here. You can see we're looking at this 3D model. Again, this is a digital surface model, and you can basically take a point tool and click on the model, and that is effectively creating a spot elevation. So just like I would do in the field, if I wanted to create a topo of this lot, I effectively walk a grid. You can see over on the left-hand side here, I'm creating a list of spot elevations, and in the bottom left there, I've got my XYZ. So basically, I would just do this on the entire project site. I can create different layers, actually draw in 3D polylines, do an automate. Yeah, there's a lot of tools in here. Just quickly show you what a finished project might look like. So using this kind of a little test project we did. So you can see a ton of spot elevations. You can do your curb lines in here, all of your different layers. Export this as a DXF, and if this is basically what you wind up with. Again, standard CAD data that comes out of it with that ortho photo behind it.
All right. Next question I have for you. Approximately how big or what percentage is the surveying drone industry relative to the entire drone industry?
That's a fantastic question. Unfortunately, we're a bit myopic. We focus pretty much exclusively on the land surveying industry. I wouldn't even want to try to make a claim about what proportion of the overall drone industry is focused on surveying. What I can confidently say is that surveyors are using drones more than almost any other industry. There's really only a couple other industries that are using a drone as where drone technology has become the norm the way it has in land surveying. Really just some kind of construction management type stuff, mines and quarries, real estate photography, Hollywood film kind of stuff. But surveyors are very much at the front of using drone technology.
Okay. Next question. How close to airports can you use a drone? Does that apply to all airports, and is that enforced?
Ooh, good question. That's another one we could talk for another hour on. So let me try to give the short version of it. As a licensed drone pilot, one of the things that you have to follow are basically classifications of airspace. So there are certain areas where there's either restricted airspace and you're not, or you have to get special authorization to fly, or where basically the kind of ceiling you can fly up to is lowered. So in open airspace, which is most places, most of the country is pretty wide open, your ceiling is 400 feet. As generally where you're going to face those restrictions is near airports. And basically the way it works is as you get closer to the airport, your ceiling comes down. So if you're, it depends on airport by airport and what their flight path is, but your ceiling come down to 350 feet, 300, 250, 200. The FAA is actually rolling out this system as we speak. I believe it's going live in California in the next month or so. That allows for basically those permissions to be granted in real time. And then for some airports, they still require getting authorization. You kind of have to apply for authorization to get those access to that airspace. So short version is you can fly pretty close to airports, basically just with a lower ceiling, and there are a handful of resources you can use to see what that ceiling is, where your project is. Different airport by airport, and it is very quickly becoming much friendlier. And the FAA is moving remarkably quickly on opening that airspace up.
Okay, and let's see, next question. Do you use Virtual Surveyor after doing the ortho photo in Pix4D?
Yes, basically we use what we output from Pix4D is that digital surface model. It's also sometimes referred to as a digital elevation model. We export that out, which effectively it's kind of like your ortho photo with elevation data underneath it. We bring that digital surface model into Virtual Surveyor, and we do the line work in Virtual Surveyor. So that's kind of a handoff. It's a handoff from Pix4D to Virtual Surveyor.
Okay. Next question on battery usage. Do you have a formula for battery used per acre, and how does that affect the accuracy?
Great question. If I flip back to the table I put up with kind of accuracy by acre expectations at different flight altitudes, that middle column, you'll see it says 1 hour of flight time. With the Phantom 4 Pro, the manufacturer, the DJI Phantom 4 Pro, that is, manufacturer spec is about 30 minutes of flight time per battery. But that's, burning the battery all the way out to zero, in which case you'd then have to throw it away. So our recommendation is realistic field expectations. You should plan for 15 to 17 minutes per battery. That makes sure you have plenty left in the tank if you have to do any sort of emergency procedures at the end of a project or end of a flight or something like that. So this 1 hour flight time is going through 4 batteries. So if your goal is high accuracy, you're going to be so you want to get to that 10th vertical or even a bit better. You can cover about 6 acres per battery. If, however, like we talked about before, if you just need to be getting to 1 foot contours, so more like, so 4/10 vertical is going to be good enough. With that same one battery and about 15 to 17 minutes of flight time, you can cover closer to 60 years, between 60 and 75 acres per battery.
Okay. Have you documented your process for determining spacing of ground control necessary?
We have, to some degree. It's a big part of the training we provide for surveyors when we do it. There's some amount of it that we kind of document and hand off to our clients, kind of some guidelines. It is something that we also wind up doing a lot of coaching for, because every project site is slightly different. And so it's a good area to expect to do some continued learning on, to see how to do that project by project.
Okay. And do you recommend performing conventional ground surveys at critical areas where you need to conform to existing conditions like a curb or gutter?
So absolutely, yes. You should always expect to do some ground survey. There are always going to be, shots that you need on a project that you need at higher accuracy than you can get out of a drone. So certainly things like building corners, that generally have to be located tighter than a tenth. And also with a building corner, in the drone imagery, because it's blocked from some angles, it's going to be somewhat lower accuracy. For curbs and gutters, it really depends on the project needs. I know a lot of our clients are comfortably relying on the drone data for a lot of curb and gutter work. Your back of curb is going to generally be really, really tight. And so a lot of times kind of best practice will be running a line on the back of curb and then offsetting to the top front of curb and offsetting again down to the flow line of the gutter. Ultimately comes down to what is the accuracy you need. If you're doing a project where it's a design project where you're going to be laying a natural gas pipeline or digging a trench and laying a natural gas pipeline down a road, and you need to know as tight as possible, how close can we get before we have to dig up the curb, you might want to collect that in the field. But the important thing to remember is it's not all or nothing. The drone is like a broad paintbrush. So even if you are doing a fair bit of field data collection conventionally, you can still rely on the drone to paint in everything else. Any of the other spot elevations you need, any of that kind of surrounding area where that 10th accuracy is acceptable, and use it as a time saver there, even while you are collecting a handful of shots in the field still.
Okay, and it looks like this is the final question. What are the current rules about flying over people?
Great question. So there's a bit of nuance here. Letter of the law is the drone cannot cross the column of air directly above a human being or moving vehicle that is not directly involved in the operation of the drone. So it's very specific. And in fact, the FAA even specified this means you can legally fly a drone right around a person, millimeters from their face, and it's totally legal as long as it doesn't cross over any part of their body. So if they stick their arm out and suddenly the drone's flying over their arm, now it was in violation. This is one where what's important here is being a safe and responsible operator. You want to mitigate risk wherever possible. Certainly if you're doing a highway project, set a brief road stop if you can for the frankly minute or less that the drone is going to be crossing over that highway. Otherwise, if you can't, then the drone's the wrong tool for that job. But the FAA is ultimately, the FAA's concern is safety, and they're very aware of things like if flying a drone over an intersection means that the drone technically crosses the path over a car that drives through, but that means you're not putting a surveyor in the middle of that intersection. That's a net benefit to safety, and so they're going to look favorably on that. So use good judgment, be safe, be careful. Know also one of the main rules the FAA is working on relaxing right now is that rule specifically for small multi-rotors. I think they're looking at under about 5 pounds. That rule will most likely be going away in the not too distant future.
I have one more question for you.
Mm-hmm.
How well can your process represent large vertical faces inherent to earthwork operations?
So near vertical faces are going to come out great. You can expect the same levels of accuracy. If it's a perfectly sheer vertical face, because the way the digital surface model works, you get water falling off the face of that. So for instance, you couldn't plan to draft in the windows on the side of a building because it's just going to waterfall off of it. If you have a bench in on an earthwork or a quarry that is perfectly vertical or even slightly concave, you're not going to be able to pull data from that. But even a pretty steep, near shear vertical face, like in most earthworks, will be fine. You can expect the same level of accuracy.
Great. It looks like that's all we have. Thank you so much for your time today. We really appreciate it. And everybody save the date for our July webinar.
Thank you so much, Kim, and thank you everybody for attending.